Okay guys, let's look at an application of how we might be able to use dot products in order to find, say, the angles that are the vertices of a triangle with given vertex values here. And so in these exercises we look at here, at least this one, number 45, it says use vectors to find the interior angles of a triangle with given vertices. Let's go ahead and kind of start just by sketching what this situation is here. And so I only did quadrant one. I noticed that these were all positive values here, but to the best of my ability, what I want to do is I want to kind of represent what this looks like here, just to get an idea of what would be true about the angles in the first place. And so what we see is this: we have 1 comma 2, we also have 3 comma 4, and so that's going to be roughly right here, and it looks like 2 comma 5. And so what I'm going to do is I'm just going to start by illustrating here these here. Now the interesting thing is that this is a triangle, but we're going to be using vectors to do this here. So 1 2, sorry, 1 2, this is 2 5, and that this is also 3 4. So the way I kind of visualize this myself is if these are all vectors, then they're definitely not in standard position here, but what would their component forms be if they were in standard position? So I'm going to refer to these vectors as u going this direction. I'm going to have v going this direction. I'm going to have w going this direction. So we have u, v, and w. And that is to say that if I were to put all of these in standard position, I kind of envision this line length here, or segment here, as starting with this one at the origin, and this being the terminal point. And then with this one here, I would imagine this being the initial point here. And so it starts at the origin and goes left and up to get to its terminal point. So it's all kind of arbitrary, but the way I have this sketch right now, I know that if I wanted to, and if I knew, say, component forms of these vectors here, I could say find the angle theta between, say, u and w here. Or likewise, I say that I've got these two vectors here. I suppose u and v making an angle with one another. What would be the angle between those two there? And so we're going to kind of take a look at how we could do this, how we could find the angle between these. I'm going to start with u and w here first, just because they're already adjoined at their initial segment here. And that's what I kind of want to look at, is the angle between those two. And so let's go ahead and start with those. What would their components be? Well, I think that that's the place we've got to start at here. If I want to find angles between vectors here, I kind of need to know what their component forms would be. And so let's start with u. In terms of u, we have its initial point and terminal point here as I have it drawn. And so as I have this drawn here, I'm going to say that u, 3 minus 1 would be its horizontal component. We always do terminal horizontal component minus initial horizontal component. I get a positive 2. And then I also get a 4 minus 2 for my vertical component. So u is 2, 2 if we have this in standard form. V then would be, let's see here, terminal x component, or terminal horizontal component minus initial horizontal component. 2 minus 3 is negative 1, whereas we do 5 minus 4 for our verticals here. We get 1. And then w, it looks like from terminal minus initial, 2 minus 1 would be a 1 here, but if we do 5 minus 2, that would be a 3. And so here are all these component forms of our vectors here. We wanted to start by finding, say, the angle between u and w here. And so I'm going to kind of just focus on these two vectors. Now keep in mind, if we are going to find the angle between these here, theta, then we need to know u dot w over the magnitude of u times the magnitude of w. So some things we're going to find first would be the dot product, but also their magnitudes. And actually, I'm just going to recommend that we do this now. So let's go ahead and find the magnitudes of u, v, and w while we're at it. Recalling that all we're really going to do is square the components of the vector, add those together, and take the square root. And so when we look at this, we say 2 squared and 2 squared are 4 and 4. You add 4 plus 4 together, we get 8, so root 8. And I know I can reduce this, but I'm going to leave it for now. Here I would get squaring negative 1 and 1, we get 1 and 1. If I add those together, I get 2, so square root of 2. And then squaring both these components, we get 1 and 9. Add those together, we get 10. So these are all of our magnitudes here. Let's go ahead and start then with this u dot w. What we end up with then is u dot w. When we talk about, say, u dot w, we're really taking u, which is 2, 2, and a dot product with w, which is 1, 3. And so writing this out, we get 2 times 1 plus 2 times 3, which is really 2 plus 6, or 8. So I'm going to throw a box around this. But what we know now is that we get a dot product of 8, which also, because it's positive, tells us that there has to be an acute angle between these. We can see that here. 8 over their magnitudes multiplied together, and their magnitudes, u and w's magnitudes respectively, are the square root of 8 and the square root of 10. So I am going to reduce this a little bit here, or at least simplify it a little bit. We get the cosine of this unknown angle is 8 over the square root of 80. And I don't care if you rationalize this or not. What I really want you to do is give me an angle in your calculator here. So we'll undo this ratio to work backwards towards the angle here. But what we get approximately is, let's see here, the cosine inverse of 8 over the square root of 80. Need a couple end parentheses here. We get about a 26.6 degree angle here. So I'm going to write 26.6 degree angle. I'm also going to come back over here on the picture and indicate that this theta right here is about 26.6 degrees. And so now maybe what I want to do is find the angle between u and v next. Now here's the thing about u and v. We're looking for this angle right here, but you notice that they're stacked head to tail. And so if I want the angle between them, what I would actually have to do is imagine that they're stacked so that their initial points are together and their terminal points are not. And so that would almost make it look like this right here, and we'd be finding this angle out here. The thing is, if we find this angle out here, what we're going to have to do is say, well, because we shifted this u over here, and this makes a 180 degree straight angle right there, if I know this exterior angle that would make over here, then I would know this interior angle by taking the exterior angle away from 180. But let's do this. Let's take u and v and just kind of see what we can make happen here. The cosine of the angle between u and v would be u dot v over the magnitude of u times the magnitude of v. And so u dot v, let's go ahead and start with this. U, which is 2, 2, we're taking that in a dot product with v, which is negative 1, 1. And this is all over their magnitudes multiplied together. So u's magnitude was the square root of 8, where v's magnitude here we can see is the square root of 2. We end up with this on top. We get 2 times negative 1 plus 2 times 1. And this presents us with a really, really kind of cool case. We get 0 over 4, which, if you remember, we're saying is equal to cosine of theta. So when we do this, we say the cosine inverse of 0 over 4 are really 0. The thing that I want you to realize is that these two vectors must be orthogonal to one another, 90 degrees. And the reason why is because remember that when you do cosine inverse and it hands you back an angle between 0 and 180, we know that cosine is only having a value of 0 on this interval at 90 degrees here. So one of our vectors is here and the other one must be up here. They must make it 90. So that means that this outside part is 90, but that also means that this inside part right here is 90, okay? So that means that if this is 90 degrees here and this is 26.6 degrees, we're just going to, do the coup de grace here, the killing blow. Add those up, minus 180. And that last angle must be 63.4. And so we're going to label this on your picture here. And so certainly we could use lot sines, lot cosines, but when you have vectors like this and initial and terminal points really if they're in standard position, then it's really convenient to use dot products to find the angles between. Cheers.